Reverse intersystem crossing, or RISC, in highly efficient TADF emitters is not a direct process. It is strictly dominated by second-order coupling, specifically the mathematical product of vibronic mixing and spin-orbit coupling. Electrical generation in OLEDs creates excitance in a ratio of about 75% triplets and 25% singlets. TADF seeks to achieve near 100% internal quantum efficiency by actively converting these triplet states, which typically waste energy, back into emissive singlet states. The process from excitation to delayed fluorescence involves several steps across different timescales. RISC, or reverse intersystem crossing, is the critical, thermally enabled bottleneck that converts triplet states back to the singlet state for delayed emission. Effective TADF requires a minimal set of states. These include the singlet charge transfer state, the triplet charge transfer state, and, critically, the triplet local excitation state, which acts as a hidden mediator. Achieving RISC requires breaking the Born-Oppenheimer approximation, which assumes electrons instantly adapt to nuclear coordinates. For RISC, nuclear motion must heavily couple distinct electronic states, as shown by the coupling region where the approximation breaks down. Direct spin-orbit coupling is insufficient in charge transfer emitters because the S1 and T1 states share nearly identical charge transfer character. This results in exceptionally weak direct SOC, meaning fast RISC cannot rely on it alone. The efficient pathway for spin flipping is a two-step chain. The triplet charge transfer state dynamically borrows local excitation character through vibronic mixing, enabling efficient spin-orbit coupling between the local excitation and the singlet charge transfer state. Effective coupling is definitively proven by the second-order perturbation equation. The numerator shows that vibronic mixing creates the necessary orbital angular momentum for spin-orbit coupling, and the energy denominators confirm that energetic near resonance boosts this coupling. Nuclear motion directly modulates electronic wave functions through non-adiabatic coupling. Torsion between donor and acceptor units and bond stretching are specific physical modes that actively shift orbital overlap, with low-frequency vibrational modes being the most effective drivers. RISC is an energetically uphill process. Thermal activation, provided by ambient temperature, populates higher vibrational levels. This physically pushes the molecule toward the vibronic resonance needed at the crossing seam, enabling the process. While minimizing the energy gap is necessary for thermal accessibility, it is insufficient for fast RISC. High-performance TADF emitters explicitly require a nearby triplet local excitation state, deliberately engineered to serve as a spin vibronic booster for a fast RISC pathway. Maximum reverse intersystem crossing demands energetic resonance. The strongest possible spin vibronic RISC occurs when the energies of the triplet local excitation and triplet charge transfer states are approximately equal. This exact resonance maximizes efficiency. Laboratory signatures confirm the spin vibronic mechanism. These include strong temperature dependence of delayed fluorescence, features in transient spectra explicitly showing local excitation, and confirmation sensitivity tied to molecular rigidity. A rigorous computational workflow is used to verify molecular designs. This involves optimizing geometries, assigning state characters, computing spin-orbit coupling elements, and calculating vibronic couplings to ultimately evaluate the RISC rates. In summary, spin vibronic TADF is dominated by second-order coupling, the product of vibronic mixing and society. Optimization requires state character engineering, and forcing energetic resonance with a triplet local excitation state acts as the definitive on switch for fast RISC.